kind of get things kicked off. Okay, just kind of doing some diagnostic tests. Okay, with the old computer. Okay, so just let's get right to it. Okay, and we have just going back to one-to-one functions and their inverses. And we have from the test for review page for the first part, okay, it says to determine the inverse as well as the domains and ranges of both the one-to-one functions and their inverses. And okay, and so we have in the case of the first item, okay, so we have a function f of x is equal to 2x plus 3 all over 5. And what we can do here, now if you notice we have a fraction with this rational expression, but the only thing we have in x is in the numerator. And so with 5 at the bottom, there's no way that we can have a zero value denominator. So x is at liberty to be any real value. It could be a negative value, 0, or any positive value. And so we can just go ahead and state that for the function. Okay, now the domain, okay, is going to be the set of all real numbers. And for what we have in the case of the range itself, okay, so y could be any negative, 0, or positive real number. Okay, so the range is also going to be the set of all real numbers. And before even determining the inverse, now what we're going to have for the inverse in x would be what is in y for the original function and vice versa. So you're going to have all the domains and the ranges will be all real numbers. Okay, so just looking at what we have in the mix, so we have f of x equal to 2x plus 3 over 5. Okay, and so again, this is a way of writing y is equal to 2x plus 3 all over 5. Okay, and looking for the inverse. Okay, so if I again look at interchanging x and y, and so we're going to have here, okay, we have the x is equal to 2y plus 3 all over 5. Okay, and we have in the case of solving for y, okay, so I can just multiply this equation by 5. Okay, so you have 5x is equal to 2y plus 3. And then we have getting the y term by itself. Okay. So if we look at taking 3 away from both sides, okay, so you have 5x minus 3 equals 2y. Okay. And then we have with division by 2, okay, and so we're going to have that 5x minus 3 all over 2 is equal to y, and I can just reverse the order. And so we're going to have for the inverse, okay, the result for this output y. Okay, so for what we have all together, okay, so the one-to-one function had all real numbers for the domain and the range, and the same thing is going to happen for the inverse. And just looking at what we have, at least from a visual standpoint. Okay, and so we have the graph of f of x is equal to 2x plus 3 all over 5. And again, just among the ordered pairs, have for this line, okay, that is red. We have -4, -1, 1, 1, 6, 3, and 11, 5. And again, we have for this black line here, okay, this is in reference to the inverse function. So you have 5, 11, 3, 6, 1, 1, and -1, -4 among the ordered pairs. And again, a one-to-one function and its inverse will have interchanging x and y terms. And again, both of these graphs will have symmetry with respect to the line y is equal to x. Okay, and all three of these lines just happen to intersect at 1, 1. All right. Now, for what we have in the case of the second function, okay, now we have a radical, okay, with f of x is equal to the square root of 2x minus 4. And for what we have in this one, okay, if you notice, we have the nature of the function is a radical, and it is an even root function. Okay, so if it's an even root, okay, you're not going to have the domain to consist of all real numbers. Okay, so we have an even root radical. Okay, so for this part, okay, now 2x minus 4 cannot be negative. Okay, now since we don't have a fraction, okay, with this expression at the bottom, it can be 0 as well as positive. Okay, so that 2x minus 4, okay, is greater than or equal to 0. And we're going to have that 2x is greater than or equal to 4. And if we divide by 2, okay, we're going to have that x is greater than or equal to 2. All right. Now, for what we have in the case of, say, for y, say y is equal to the square root of 2x minus 4. Okay, now, again, there's a rule. Again, that's the principal square root rule. Which states, that the even roots of an expression cannot reduce to a negative constant. It can reduce to a 0 as well as to a positive. Okay, so that means here that for what we're going to have in the case of y, so y equals the square root of 2x minus 4, and that radical can reduce to 0 or higher. So you're going to have that y is greater than or equal to 0. Okay. And so just for what we have in the case of the function f of x, Okay, so we have for the domain, okay, values of x greater than or equal to 2, and utilizing interval notation. Okay, so you have starting from and including 2. We have going out to approaching infinity. And for what we have in the case of the range, okay, so we have going from and including 0, and we have moving continuously higher. Okay, so it'll be the domain and the range of our given one-to-one function. Again, looking for the inverse. Okay, so writing this function implicitly, so you have y is equal to the square root of 2x minus 4. And again, just interchanging x and y. So we're going to have the x is equal to the square root of 2y minus 4. And okay, so I want to solve for y, but right now we have this is part of the expression 2y minus 4, which we have in the square root. So I can eliminate the presence of the square root upon squaring both sides. All right, and so I have x squared equal to 2y minus 4. And getting the y term by itself. Okay, so I have x squared plus 4 is equal to 2y. And dividing by 2. Okay, so we have x squared plus 4 over 2 is equal to y. So I have y is equal to x squared plus 4 all over 2. And just for the inverse, just to restate and putting in formal functional notation, so you have the inverse of f of x is equal to x squared plus 4 all over 2. And there is an added twist because concerning the domains and the ranges, okay, again, we do not have all real numbers throughout. So just again, we started out, okay, with this radical function. Now again, for the domain of the inverse, okay, now again, okay, had this been our one-to-one function to start with, or I'll tell you what, just for the inverse function, okay, so the domain, well, we have an x would be what was in y for the radical function. Okay, so we're looking at set of values x greater than or equal to 0. And for what we have in the case of the range, okay, we have going from and including y is equal to 2 all the way out to infinity. Just providing a visual also on this one. Okay, so just taking what we have with this graph, I'm trying to zoom in here. Okay, so you have, if you notice, you have y is equal to the square root of 2x minus 4. So I have this particular curve, okay, so you have among the order pairs, you have 2, 0, 4, 2, and 10, 4. And for the inverse, okay, you have y is equal to x squared plus 4 over 2, but I don't need the whole parabola. And to make this one-to-one with respect to the original function, okay, again, just to comply with the domain of this quadratic function, okay, it has to be values of x greater than or equal to 0. So adding in this detail, okay, I'm limiting this to just the right half of the parabola in order to make that parabola one-to-one, and also the inverse of the radical. Okay, so if you notice, you have the order pair, we have 0, 2, in contrast to 2, 0, 2, 4 with respect to 4, 2, and 4, 10 with respect to 10, 4. And again, you have infinitely many other ordered pairs that can be applied, and both of these graphs will have symmetry with respect to the line y is equal to x. All right, so again, you have just those samples of one-to-one functions and their inverses. And now, kind of going back to what we have with properties of logarithms. Okay, and it says to evaluate the following expressions, and tell you what, it says to find, oh, my bad, yeah, it says to evaluate each of the logarithmic expressions and equations. And we have for the third item, now we're looking at the base 5 logarithm of 26. Okay, and this is going to go back to the change of base formula, okay, throughout. And for what we have in the mix, okay, so we got for that one, so yeah, with our properties, let me go and write these down. Okay, so you have okay, so the base 5 logarithm of 26. You have the base 7 logarithm of 19 over 13. And we have the base 3 logarithm of 38 thirds. Okay, now again for numbers 3 through 5, okay, so you have the change of base formula. And this, once again, is where if you have the base A logarithm of m, okay, it's going to be the base B logarithm of m all over the base B logarithm of A, and the base B logarithm can either be the natural or base 10 logarithm. Okay, now for what we have in the case of this problem set, okay, so we're looking at the base 5 logarithm of 26. Okay, and again, we have m is represented by 26 and a by 5. And now for the base 5 logarithm of 26, you can either use natural or base 10 logarithms. It's still going to be the same reduction. And we just go with natural logarithm on this one. Okay, so you have natural logarithm of 26. all over the natural logarithm of 5. And again, you had to enter natural logarithm twice, once for 26 and again for the natural logarithm of 5. And we have to about the nearest 3 decimal places. Again, that's going to come out to about a 2.024. Okay, now in the case of the natural logarithm, or the base 7 logarithm of 19/13. Okay, now again, you can either use natural or base 10 logarithms. And let's go with base 10 on this one. Okay. And for what we have on this one, okay, so you have the base 10 logarithm of 19/13. Okay, we have over the base 10 logarithm of 7. Okay, and in terms of how this might appear, okay, if you can program in the log into your calculator. Okay, so we got a fraction for one of the attachments. So you have like the base 10 logarithm 19/13. Close out, and then you have another forward slash to signal division by the base 10 logarithm of 7. And to about the nearest 3 decimal places. Okay, that's just going to be a little bit under 2/10, right at 0.195. And for what we have in the case of the base 3 logarithm of 38/3, and we'll go with the natural logarithm on this one, but I could have repeated the use of base 10 logs. Okay, so here your m is 38/3 and your a is at 3. So just reformatting, have the natural logarithm of m over the natural logarithm of a, and just using a little bit of the handwritten counterpart of the calculator notation. Okay, so have the natural logarithm of 38/3. Then we have all over, okay, the natural logarithm of 3. And for this value, okay, this will come out to about 2.311. All right. Now, just kind of looking at what we have with, we'll get back to number 6, okay, but for what we have in the case of items 7 and 8 in this group. Okay, so we're looking at expressing sums and differences of logarithms and expressing powers as coefficient factors. Okay, and now 7 and 8, okay, those are a little bit tricky because you have radicals that are in the mix. Okay, now just going back to our properties once again. So you have the base A logarithm of m times n. Okay, so you have the base A logarithm of m plus the base A logarithm of n. And for division, okay, so you have the base A logarithm of m minus the base A logarithm of n. Okay. And again, the converse is going to ring true. Just Yeah, so in the reverse, okay, so you have addition is going to imply multiplication in the attachment whenever you're consolidating as a single base A logarithmic term. And again, subtraction implies division. Okay, now in terms of expanding logarithmic terms, okay, so we have in the case of item number 7, okay, so you have a base 3 logarithmic term, and we have in the attachment now we have various factors here. So you have x squared, and we have times the cubic root of y to the 5th, and we have times the 6th root of z, and we have all over 9 times the 4th root of b. All right, now what I can do here is that before I look at expanding, okay, so I have with these radicals, I can write these as non-integer powers. Okay, so you have for the factors here, so I have x squared. Now for the cubic root of y to the 5th, now if you remember, you have like the nth root of a to the m is equal to a to the m over n. So you have the inside power divided by the index number. Okay, so in this case, we're going to have y to the 5/3 and the 6th root of z, or the 6th root of z to the 1st. Okay, this is going to be z to the 1/6. And we have 9. Now we have for the 4th root of b, or the 4th root of b to the 1st. Okay, that is going to be b to the 1/4. Okay, and notice we have simultaneous multiplication and division going on. And what I will do is I will take with the top terms or factors. Okay, we'll go ahead and write these out in the initial expanded form. So anything that is at the top, okay, will be attachments of positive base 3 logarithmic terms. So we have a base 3 logarithm of x squared, and we have plus the base 3 logarithm of y to the 5/3, and we have plus the base 3 logarithm of z to the 1/6. Okay. And now for what I have at the bottom, okay, in the expanded notation, okay, 9 and b to the 1/4 will be attachments to negative base 3 logarithmic terms again. So you have anything that is in the denominator, there will be attachments of negative logarithmic terms in the expansion. So here we'll have minus the base 3 logarithm of 9. And we have minus the base 3 logarithm of b to the 1/4. All right. And writing the powers as coefficients. Notice we have x to the 2nd, so I can move the 2 for y to the 5/3. Okay, the 5/3 can be shifted. For z to the 1/6, okay, we move 1/6 to the front, and we have another exponent. Okay, we have with b to the 1/4, so I can move b to the 1/4 at the front. And for what we have in the case of the base 3 logarithm of 9, okay, now 9 relative to 3, okay, it is both a multiple and an integer power of 3. So I just mentioned this one in case you had the base 3 logarithm of 9. Okay, so in terms of base 3, okay, so 9 is going to be 3 to the 2nd. And again, a base A logarithm of a to the x goes to x in this case, right? So this is going to go to 2. So for what we are going to have in the follow-through, okay, so first term we have 2 times 3 to the 2nd. Okay, so 2 to the 2nd, okay, so 2 to the 2nd is going to be 2 to the 2nd. Okay, so 2 to the 2nd the base 3 logarithm of x. Next, okay, so we have plus 5/3 the base 3 logarithm of y. And we have plus 1/6 the base 3 logarithm of z. Okay, and then we have minus 2. And then we have minus 1/4 the base 3 logarithm of b. Okay, and so we have in the fully expanded notation, okay, this is what we're going to have among the terms here, and they don't have to be in exactly that order, but I just had it arranged where the positive terms would come before the negatives, but you could have those terms in jumbled or even reverse array, as long as you got those two terms to be negative and these three to be positive. Okay, and now for what we have in the case of number 8, okay, we have in the mix. And we have, this time around, say have a base 5 logarithm and this is of 7x squared times y to the third. And we have all over w to the fourth times the square root of z squared plus 5. And what I'll do here is I'm just going to rewrite the radical. Okay, so I have base 5 logarithm of 7x squared y cubed, and we have all over w to the fourth, and we have with the square root of z squared plus 5, we can say we have this binomial is raised to the 1/2 power. All right. And so looking at expanding, okay, so I'll just go with the terms at the top first of all. So you have 3 factors of 7x squared and y to the third. So the base 5 logarithm of 7. And I have plus the base 5 logarithm of x squared and you have plus the base 5 logarithm of y to the third. Okay, and with w to the fourth and the square root of z squared plus 5 at the bottom, okay, we have these to exist individually as negative base 5 logarithms. So we have minus the base 5 logarithm of w to the fourth, and we're going to have minus the base 5 logarithm of z squared plus 5 quantity to the 1/2. Okay, and just looking at what we have among the terms now, and the base 5 logarithm of 7. 7 is not a multiple or an integer power 5, so this number is already in simplified exact form. Okay, and we have x squared, so we move the 2. For y to the third, I can move the 3. And I can move the 4 from w to the fourth, and with z squared plus 5 quantity to the 1/2, I can move this to the front of the log. Okay, and so we have in the expanded notation, so we're going to come out to the base 5 logarithm of 7, and we have plus 2 times base 5 logarithm of x, and I have plus 3 times the base 5 logarithm of y, and I have minus 4 times the base 5 logarithm of w, and we have minus 1/2 of the base 5 logarithm, okay, and we have of the quantity of z squared plus 5, okay, and now z squared plus 5, again, that attachment stays in parentheses, and this is all you do to this one. So z squared plus 5 stays as it is. You don't distribute, like having like this of z squared plus that of 5, okay, and the 2 in the z squared, that is going to stay, okay. So the attachment z squared plus 5, and the only exponent you had to move was that which was in reference to the radical, namely 1/2, okay. And so that is going to be the finalized expanded form of what we have in the case of this problem. Okay, now we'll be looking at going from expanding to combining logarithmic terms, okay. And so for what we have in the case of these items, and tell you what, let me okay, so looking at combining logarithmic terms, and let me give you just a couple of quick cases here. And also going to have in the mix, okay, it's just among your properties, okay. Again, we had this situation where you might have they're the same case. So you have like r times the base a logarithm of m and that's going to be equal to the base a logarithm of m to the r. So this is like going from coefficient to power. And let's say if we're looking at writing as a single logarithm, okay, and let's say that if we have something like say something like 3 times the base 4 logarithm of 2, and we'll say we have minus the base 4 logarithm of u minus 3 times the base 4 logarithm of x and we'll say we have plus 4 times, okay, the base 4 logarithm of z. Okay, so what I can do here is kind of going in the opposite direction. So for the leading coefficients, I can write as exponents. Okay, so for 3, base 4 logarithm of 2, saying the base 4 logarithm of 2 to the third so in other words, kind of going in the opposite direction here. So I had base 4 logarithm of 2 to the third, and right now we got minus the base 4 logarithm of u, no exponent to move, and for 3, base 4 logarithm of x, again I can move the 3, so you have minus the base 4 logarithm of x to the third, and we have plus the base 4 logarithm of z to the 4th. Okay, so for what I have here, okay, so you have the base 4 logarithm, and looking at what we have in the attachments. Okay, so you have base 4 logarithm of 2 to the 3rd. Okay, that's part of positive. The 2 to the 3rd, okay, is part of a positive base 4 logarithm, so that part goes to the top. Now for u, this is part of a negative base 4 logarithm. Okay, so this will be an attachment in the denominator. And likewise for x cubed, this is part of a negative base 4 logarithmic term, so that will go on the bottom. And we have plus base 4 logarithm of z to the 4th. Okay, this is part of a positive logarithmic term, so z to the 4th goes on the top. And just little adjustments. Now if you had this as your final answer, I would count that correctly as correct. But just for 2 to the 3rd, okay, that's going to be 8 z to the 4th and again we have all over u times x to the 3rd. Okay, and now just where we have as single logarithms, and I said that we would get back to item number 6, okay, for this part 1 set. Okay, and it says to evaluate each of the logarithmic expressions and equations. Okay, and it says if the result is not an integer or a terminating decimal. Okay, and it says to round to the nearest 3 places. Now we've already looked at numbers 3 through 5 in that particular set, and we have now with number 6. Notice you have base 54 logarithms. Okay, and you have 2 terms added, one of which is going to be subtracted. So you're going to have a blend of combining logarithmic terms in line with the sum and difference properties, as well as utilizing the change of base formula. Okay, so looking at consolidating what we have in the case of number 6. All right, so with number 6 relative to what we had in numbers 3 through 5, again there was an added ingredient, and again that is with the sum and difference properties. Okay, so again we have the base 54 logarithm of 19 and we have plus the base 54 logarithm of 25 and we have minus the base 54 logarithm of 10 . Okay, and so we have with these terms, okay, so we're looking at numbers, okay, and now for addition, and addition is going to imply multiplication, and subtraction is going to imply division. Okay, so 19, 25, and 10, none of those terms will be multiples or integer powers of 54. So what we can do here is that we can go ahead and consolidate as a single base 54 logarithmic term. Okay, so you have first term, okay, 19 is part of a positive base 54 logarithm. And guess what? 25 is as well. So you're going to have 19 times 25. Now for the base 54 logarithm of 10, okay, that term is negative, so 10 is going to go on the bottom. And for what we have in following through, okay, so you got 19 times 25 is 475, and 475 divided by 10, okay, that's going to be 47 and a half. And again, where the change of base formula is going to come in, again, you can either use a natural or a base 10 logarithm. Okay, and for what we have in this, we'll just go with the natural logarithm. Okay, and again, just using this part of the change of base formula. So just putting this in terms of natural logarithm. So your m is at 47.5. And your a is at 54. And so we'll have for this output to about the nearest 3 decimal places. Okay, this is going to be right at 0.968. And now, in terms of what we have with the group, where we have where it definitely says to combine as a single logarithm. And we have for numbers 10 through 12 in this one case. So if we write the expression as a single logarithm, all that, and we'll say here, we'll go with, say, for numbers 10 and 11. Okay, so you have 2 times the base 5 logarithm of 10 plus 3 times the base 5 logarithm of x minus 2 times, okay, the base 5 logarithm of y. Okay, so for what we have in the case of number 10, okay. Okay, so I have 2 times the base 5 logarithm of 10 plus 3 times the base 5 logarithm of x minus, okay, 2 times, okay, the base 5 logarithm of y okay. And as we look at consolidating as single terms in the mix, okay, so we got looking at converting from coefficients to exponents. So you had the base 5 logarithm of 10 squared plus the base 5 logarithm of x cubed. You have minus the base 5 logarithm of y squared and just looking at consolidating once again. So you have 10 squared, okay, comes from a positive base 10 logarithmic term, and so does x cubed. And for y squared, again, this originates from a negative base 5 logarithmic term. Okay, so this could be one display of your final answer, but just sort of specifying. Okay, so you have 10 squared is going to be 100. And we have times x cubed, and we have all over y to the second. All right. Now, for what we have in the case of number 11. Okay, so you have 2 times, okay, the natural logarithm of u, and we have plus 3 times, okay, the natural logarithm of v, and we have plus 1/2 of the natural logarithm of the quantity of u plus v. We have minus 3/4 of the natural logarithm of w to the 4th plus y to the 5th minus z. Okay, so if you notice for all four of these terms, okay, so we've got coefficients in front of the ln. Okay, so we can make those coefficients into exponents. Okay, so for the first term, we'll have the natural logarithm of u to the 2nd. And we have plus the natural logarithm of v to the 3rd. We have plus the natural logarithm of the quantity of u plus v raised to the 1/2. You have minus the natural logarithm of the quantity of w to the 4th plus y to the 5th minus z. Okay, we have all raised, okay, to the 3/4. All right, and so just looking at having shifted the coefficients over to exponential position, okay, I can go ahead and consolidate the attachments. Okay, so you have the first three terms are positive. So u to the 2nd v cubed and u plus v to the 1/2 are going to go to the top, and with the last term as a negative, okay, this attachment is going to go on the bottom. And another way you could write this, where you have the non-integer exponents, if I had to express as a radical. Okay, so this would be u squared v to the 3rd, and u plus v to the 1/2. Okay, that is going to be the square root of u plus v. And then we have in the denominator. Okay, so with the 3/4 degree, now the 4 is going to be the index number. So we have a 4th root, and it's going to be the 4th root of what? Well, it's going to be the 4th root of the cube of this collection. Okay, so this is another way that this result can abound. Okay, now for what we have in the case of working with taking what we have with kind of going back to the interchanging, okay, or transitioning rather, going from exponential to logarithmic functions. Okay, now this probably seems about like a broken record, but as I'm going back, but again, we have f of x equal to a to the x, but in between the introduction and the finalization with the inverse notation, there are a couple of steps in between that I do want to tie in together. Okay, so you got y is equal to a to the x. Again, we have x is equal to a to the y. And again, just taking the base A logarithmic terms on both sides. just shuffling once again. Okay. So you have y is equal to the base A logarithm of x okay. And for what we have, just like for the in-between steps, okay, so you have, after interchanging, I had x is equal to a to the y. And as I wrote this equation in terms of y, so I have y is equal to the base A logarithm of x. And there is a property, okay, that's going to involve solving exponential as well as logarithmic equations, okay. And here we're going to have that y is equal to the base A logarithm of x if and only if x is equal to a to the y. Now you still have regarding for the a's in both capacities as logarithmic as well as exponential base. Again, you have a as any positive value except for 1. And for what we have in the case of x, now x is still going to be positive. Okay, and all right. Now, just taking samples of what we have with these items. Okay, so if I express in terms of a logarithm or exponent, okay, so just I'm just kind of give you a little bit of a visual guideline. Okay, so you have, again, you have on the one hand, you have y is equal to the base A logarithm of x. And we have x is equal to a to the y. And we'll say we have for the first item, okay, we'll say that we have that 3 is equal to the base 5 logarithm of 125. Okay, so you might have like in your textbook or as an Alex exercise, you might have like base 5 logarithm of 125 is equal to 3. And you can just take the commutative property, switch the size to have it in the y is equal to the base A logarithm of x format. Okay, so for the equivalent on this in exponential terms, notice your x is 125, okay, your a is at 5, and your y is at 3. So guess what? Reformatting. So x, we got 125 is equal to 5 and to the y, which is going to be at 3. And guess what? This logarithmic term translates to a true exponential statement where 125 is indeed equal to 5 to the third. Okay. And let's say that if you have, as a second case, now we'll just present the exponential statement. Say we have something like 16 is equal to 4 raised to the second. So x is at 16, a is at 4, y is at 2. And so for y, okay, so that's going to be 2. Your logarithmic base is going to be at 4. So 2 is going to be equal to the base 4 logarithm of 16. And that would be a logical consistency, because like 16 in terms of base 4, you have like the base 4 logarithm of 4 squared, and that reduces to 2. Okay. So very much in line with what we have looked at so far with properties of logarithms from the start. Now if we have, let's say, once again, if you have implicit logarithmic bases, okay, so you have 3 is equal to log of 1,000. And again, just as a reminder, now if you see just log, okay, that's going to make reference to a base 10 logarithm. So 3 is going to be the base 10 logarithm of 1,000, and then just translating this out to the exponential equivalent. Okay, so your x is at 1,000. And for a to the y, so your a is going to be at 10. And to the y, so that is going to be at 3. So 1,000 is equal to 10 raised to the third power. Again, where we have also given implicitly, okay, if you have that t is equal to e to the 5th. Okay, so that e number, that's that 2.718 figure that runs endlessly. And again, e is going to be the natural logarithmic exponential base. So what I can do here, so x is at t, a is at e, y is at 5. Okay, and then just reordering in terms of y is equal to the base a logarithm of x. So for y, I have it 5. And base a is going to be the logarithmic base e. And we have x, which I have represented by the letter t. So the equivalent in logarithmic terms, you can say 5 is equal to the base e logarithm of t, or again, base e logarithms are going to be natural logarithms. So in this case, we have that 5 is equal to the natural logarithm of t. All right, now where we have, we might have more than one term to represent any one of y, a, or x. Okay, and let's say if we have something like let's say we have 2y plus 4 is equal to the base 5 logarithm of u. All right, so here you have y represented by the binomial 2y plus 4. A is going to be at 5. X is going to be with the letter u. Okay, so we have for putting in exponential format with along the lines of x is equal to a to the y. So x we have at u. Doing a little color coding here. Okay, so you have u is equal to, now for a, okay, so that's going to be 5. We have 2 to the y, so that's going to be 5 to the 2y plus 4 degree. And let's say that if we have for item 6, okay, let's say if we have, yes. Okay, say we have for number 6, in case you have negative 5. Is equal to the base 2 logarithm of 1 over 32. Okay, so you have a negative value involved. Okay, so y is at negative 5, a is going to be at 2, x will be at 1 over 32. And if I rearrange, so your x is this fraction, 1 over 32. And a is going to be at 2 to the y, so 1 over 32 is equal to 2 raised to the negative 5th, or 2 to the negative 5. And for what we have in the case of number 7, okay, say if I have that 2 is equal to the natural logarithm of x. Okay, and I put this in exponential terms. Okay, so for 2 is equal to the natural logarithm of x, again, if I had to specify the base logarithm explicitly, so a natural logarithm is going to be a base e logarithm. So for 2 is equal to the natural logarithm of x, we're going to have that 2 is equal to the base e logarithm of x. And so for x is equal to a to the y, so we got x as x. And for a to the y, your a is going to be at e. And again, that is going to be to the second power. All right. And now, just another backdrop. And we have, in the case of kind of making a transition from logarithmic and exponential terms and heading on over into equations. Okay, and so we have in this one, so you have for exponential equations with a common base. Okay, so for exponential equations with a common base, I'll show you what I mean by this. Okay, those are going to be exponential equations you will be able to solve without having to use a calculator, or likely will not have to use a calculator. Say if you're looking at solving for x, and let's say we have, now some equations might have more than just one common base. But we'll kind of start off with something with fairly low digits. Okay, so it has something like 2 to the x is equal to 8. And I wrote this equation in terms of a common base. And if you notice, 8 is a multiple of 2, and it is also a power of 2. All right, so you have, between these items, okay, we have a common base with 2. Now the left hand side we have in terms of base 2. So you have 2 to the x. And for 8 is going to be 2 raised to the third. And anytime I have single terms on both sides and they had the same base, I can now set the powers equal to each other. In this case, we're going to have for the outcome, x is equal to 3. Now, let's say that if there's a common base, but it is not yet present in the introduction of the equation. And let's say we have something like 9 to the x is equal to 27. Now 27 is a multiple of 9, but it is not an integer power of 9. But now for both 9 and 27, okay, both of these are multiples as well as integer powers of the number 3. So if I rewrite both 9 and 27 in terms of base 3, guess what? We have for 9 to the x. 9 is going to be at 3 to the second. And 9 to the x is going to be 3 squared to the x. And for 27, now 27 is going to be 3 raised to the third power. And so we got both of these expressions in terms of base 3. Now for 3 squared to the x, okay, so 9 to the x is 3 squared to the x. And I can take the power property. So I've got 3 to the 2 to the x. That's going to be 3 raised to the 2 times x. And that is equal to 3 to the third. So I have single base 3 terms. And if I set the powers equal to each other, okay, so we're going to have that 2x is equal to 3. And with division by 2, I can say that x is equal to 3 halves, or 1.5. And in a sense, you can check your results. So if I took 9 to the 1.5 or 9 to the 3 halves, and do not forget to put 3 halves in parentheses if you use the fractional exponent, and the output is going to come out to 27. And now for what we have for exponential equations with a common base, I'll give you just a couple more here. And we'll say something like 4 to the x plus 3 is equal to 8 raised to the x minus 2. Okay, so 8 is a multiple of 4, but it's not an integer power of 4. But we do have both 4 and 8 to be as such with respect to base 2. So for 4 to the x plus 3, now 4 is going to be 2 squared. We have taken to the x plus 3. And for 8 is going to be at 2 cubed. And we have to the x minus 2. Now we have in the process, now we have with the power property, now we have 2, and this will be to the 2 times all of x plus 3. And for 8 to the x minus 2, so we got 2 cubed to the x minus 2, so that's going to be 2 to the 3 times all of x minus 2. And looking at what we have now, so we got 2 and 2 over x plus 3, so this will be 2x plus 6. And we have for 2 to the 3x minus 2, okay, so that is going to be 2 raised to the 3x minus 6. And if you notice, we have single base 2 terms, and we can set the powers equal to each other. So now we have 2x plus 6 is equal to 3x minus 6. And looking at solving for x, okay, so I have a couple of x terms. And what I'll do here is I'll just take out the smaller x term to get this to go out. And I can just kind of simultaneously add the constant 6 to both sides. So we have, in this instance, okay, so you have 6 plus 6 is 12. And 3x minus 2x becomes x. And so in this case, the value x in this instance is going to come out to 12. And in a sense, you could check, okay, have like 12 plus 3 is 15, and 4 to the 15th would be equal to 8 raised to the 10th power. Now you have some large numbers here, but this is where the consistency is going to lie. And let me give you, like just with this fourth case, if I have something like 9 to the x times 3 to the x minus 1, and say we have is equal to 27 to the 2x. Okay, so you're going to have the common base to be at 3. For 9 to the x, 9 to the x is going to be 3 squared to the x, and we got already 3 to the x minus 1 with the base 3. And for 27 to the 2x, 27 is 3 cubed raised to the 2x. And just looking at what we have here, 3 squared to the x is 3 to the 2x. And we got times 3 to the x minus 1. And 3 to the 3 times 2x, well, that is going to be 3 to the 6x. And we're just about there. Okay. So 3 to the 6x. Notice we have two base 3 terms on the left, and I'm going to put these together with the product property. So here I'm going to add the exponents together. Okay, so now I got 3 to the 3x minus 1 is equal to 3 to the 6x. Now I got single base 3 terms. And I can set the powers equal to each other. So with 3x minus 1 equal to 6x, I can take 3x away from both sides. And we've got -1 is equal to 3x. And we have with division by 3. Okay, so we can come out to a non-integer value for x, and that is going to be at -1/3.